Welcome to this explainer. When you look up at those massive steel towers and thick wires crisscrossing the landscape, it's pretty easy to just think of the power grid as a static delivery system, right? Just wires on poles. But honestly, that couldn't be further from the truth. In reality, you are looking at the largest, most dynamically balanced machine on planet Earth. Literally every single second of every single day, the exact amount of electricity being consumed has to be perfectly matched by the electricity being generated. It is this constant, super delicate, high wire balancing act of physics and engineering. And that brings us to what might just be the most pressing question of our generation. What actually happens to our safety, our stability, and really our everyday lives when our transition to green energy completely disrupts the historical physics that this entire grid was built upon? I mean, we are fundamentally changing how we generate power. We're moving away from these massive, heavy, spinning turbines and moving toward lightweight digital solar panels and wind inverters. And while this shift is absolutely incredible for the environment, it is pushing this delicate machine to its absolute limits. So, here's our addenda for today. First, we'll look at the power supply chain. Second, the anatomy of transmission lines. Third, the grid stability challenge. Fourth, fixing renewable integration. And finally, substation grounding and safety. Let's get right into it. Section 1. The power supply chain. Okay, to truly grasp the challenges of the modern grid, we have to start by zooming out. We need to look at how power actually travels from a spinning generator all the way to that outlet in your wall. We rely on this massive supply chain that's managed by independent system operators and regional transmission organizations. As you can see, there are three primary segments here: generation, transmission, and distribution. These operators have to constantly monitor the high-voltage transmission lines that connect different regions just to make sure power moves efficiently over super long distances before it's finally distributed to commercial, residential, and industrial end users. Let's break that flow down into four distinct steps. Step 1 is generation. So in a traditional power station, a rotor spins inside a stator, generating electricity at roughly 22 kilovolts. But here's the thing, you can't push 22 kilovolts across the entire country efficiently. So step 2, it hits a step-up substation that jacks that voltage way up. We're talking 345, 500, or even 765 kilovolts for long-distance, high-voltage transmission. Then, step 3 is subtransmission, where power moves regionally at slightly lower high voltages, like 69 kilovolts. And finally, step 4 is distribution. This is where step-down substations drop the voltage back down to safe levels, usually below 34 kilovolts, to feed the circuits that run right through our own neighborhoods. Section 2. Anatomy of transmission lines. Now, when we look at the physical structures that carry these massive loads across the country, it's pretty fascinating to see how their physical size and design scale directly with their voltage capacity. Take a look at the far left. You've got this towering lattice steel superstructure, and that is required to safely carry a massive 500 kilovolts. But as you move to the right, the voltage drops to 230 kilovolts, then 138, and you can see the structures become noticeably smaller and simpler. By the time we reach the distribution level at 13 to 7 kilovolts, while we're looking at those standard wooden utility poles you probably have out on your street right now, it really shows how the physics of voltage literally dictates the physical world we build around it. Section 3. The Grid Stability Challenge. For over a century, this whole system worked perfectly, and it was all based on the physics of large, centralized power plants. But as we transition to distributed renewable energy, we are fundamentally altering the invisible forces that hold this whole thing together. To understand why, we have to talk about inertia. I want you to think of grid inertia like a giant, super heavy spinning flywheel. Traditional fossil fuel or nuclear generators rely on these massive physical turbines. Because they're incredibly heavy and already spinning, they naturally resist any sudden changes. So if a power line goes down or demand suddenly spikes, the sheer momentum of those spinning turbines buys the grid critical seconds to adjust without the frequency dropping. But modern solar panels and wind turbines, they're totally different. They connect to the grid through digital power electronic converters, or inverters. They are lightweight, they completely lack this physical momentum. And the crucial point is right here. Just look at how steeply the grid's frequency deviation climbs as renewable penetration increases. Down at 10 or 20% renewable energy, the deviation is minimal because those old heavy spinning machines are still carrying the load. But when renewable penetration hits 70%, the frequency deviation spikes dangerously high. Without that physical flywheel effect, the rate of change of frequency, engineers call this Rohkopf, happens so insanely fast that it can actually trigger under-frequency load shedding, which, by the way, is just technical jargon for rolling blackouts. And it's not just frequency we have to worry about, it's also transient stability. The math you're looking at here models power transfer and the system's ability to remain synchronized after a large disturbance, like a short circuit. Because inverter-based renewables provide really limited fault current compared to those old conventional generators, our transient stability margin is drastically lowered. To put it simply, lightweight renewables just lack the raw brute force to punch through a disturbance. And that means a sudden fault is way more likely to trigger cascading failures across the whole entire system. That delicate balance, it's completely lost.
Section 4. Fixing renewable integration.
I know, this all sounds a bit alarming, right? If we're literally stripping the grid of its physical flywheel, how on earth do engineers keep the lights on and stop the system from collapsing? Well, the solutions are actually ingenious. Engineers are basically fighting physics with advanced software and new hardware. To combat that frequency instability caused by low system inertia, they're deploying something called virtual inertia control. This is where smart inverters detect a frequency drop and instantaneously inject stored power to artificially emulate that physical resistance we used to get from heavy spinning metal. We're also seeing the rise of grid-forming inverters. These are devices that don't just follow the grid's frequency, they actually help establish and stabilize it. So we're replacing mechanical mass with digital speed. Section 5. Substation grounding and safety. Finally, let's zoom all the way down from these huge macro-level challenges to just a single node, the substation. Because when grid instability leads to a fault, managing that massive surge of rogue electricity is literally a matter of life and death for the people standing on the ground. When a short circuit or a lightning strike hits a substation, the fault current dumps directly into the earth, and this creates something called ground potential rise, meaning the actual dirt you are standing on can carry vastly different voltage levels from one spot to another. Step voltage is the dangerous difference in electrical potential between your 2 feet when you take a step. Mesh voltage is the potential difference between a grounded piece of equipment you might be touching and the ground right beneath your feet. Without proper engineering, just walking through a substation during a fault could electrocute you. So, to protect human lives, engineers use incredibly dense math, like this IEEE geometric equation, which is used to calculate corrective factors for current irregularity. They literally have to calculate exactly how a fault current will split, how fast it's going to decay, the specific resistance of the local soil, and exactly how that energy will travel through the earth. They map out the exact geometry of the substation just to ensure that the mesh and step voltages never, ever exceed what a human heart can withstand. And that mathematical solution becomes a physical reality, a massive, buried matrix of interconnected copper cables and deep ground rods. This entire grid is buried right under the crushed rock of the substation. When a massive fault current enters, this grid safely captures it and evenly disperses that deadly voltage deep, deep into the earth. It lowers the resistance and ensures that the surface voltage remains completely flattened, which keeps anyone walking above ground entirely safe. So what you should really take away from this explainer is that maintaining our modern power grid requires absolute top-tier engineering on literally every single scale. Up on a national level, we're navigating the loss of physical inertia from fossil fuels and replacing that old mechanical reliability with lightning-fast software, virtual inertia, and grid-forming inverters. And on a micro level, engineers are deploying these highly calculated physical safety nets buried deep in the earth just to tame the immense forces of electricity and keep us safe. It really leaves us with a fascinating high-stakes challenge for the future. As we continue to remove the old, heavy spinning machines that basically built our modern world, can we successfully program a safer, greener grid that never loses its balance? It's a monumental task, but as we've seen today, the engineering and the math are absolutely rising to meet it. Thanks for exploring the delicate machine of our modern grid with me, and always keep questioning how the world around you actually works.